got you guys pinched in there right now.
Okay, do we have access out? Can we make it out right now?
That's negative. When we came through, the fire was about 50 feet from the road.
The Black Tiger Fire, 44 homes lost. The Butte Fire, 72 fire shelters were deployed. The Mack Lake Fire, 1 fatality. The Paint Fire, 551 homes destroyed. The Dude Fire, 6 firefighters died. Sometimes Mother Nature can cause some very sudden changes in the direction and intensity of a fire. In a very short period of time, a fairly calm fire situation can turn into a life-threatening ordeal. Someday, you as a firefighter might find yourself retreating from an oncoming wall of flame. What you're about to learn can give you some warning signs that might clue you into possible trouble. Warning signs that could save your life. Understanding fire weather is vitally important to you as a firefighter. As our knowledge of fire and fire behavior increases, fire is becoming less and less a wild and mysterious force, and more, a calculated and predictable occurrence. By understanding weather's role in fire behavior, we're taking a giant step towards safe and injury-free firefighting. Weather, as it relates to fire, can be broken down into 3 basic topic areas. There are winds, moisture, which includes relative humidity and fuel moisture, and atmospheric stability. All of the factors and variables that come together to produce our weather can at times seem very complicated. If, however, we break weather down into its basic parts, we find it's built on some very simple concepts. By understanding the fundamental components that make up wind, moisture, and atmospheric stability, you'll start building a foundation of fire weather knowledge that'll last throughout your career as wildland firefighters. Obviously, winds have a very pronounced effect on how a fire will behave. Today, we'll discuss 3 different types of wind. Winds that blow on a large scale across the continent, winds that are generated by the buildup of thunderstorms, and winds that are produced on a very small, localized scale. But first, let's lay some groundwork. The very thin blue layer of gases that surrounds our Earth is called our atmosphere. This atmosphere is divided into a number of sublayers that are characterized by differences in temperature. The layer closest to the Earth is called the troposphere. It is within this layer that all the constantly changing weather that affects us every day takes place. A very simple principle accounts for most of our weather. That being that hot air rises and cold air sinks. As the air above this campfire is heated, it rises. As it cools, it sinks back down and is pulled in to replace the rising heated air. This cycle sets up what is called a circulation cell. Because the sun heats the equator more than the poles, the Earth produces a similar circulation pattern. As the warm air rises and spreads out at the equator, The rising air creates a void, or a low pressure area. Cooler air from the polar region is pulled in to fill up that void or low pressure area. This forms a completed circulation cell. Sometimes a hot air mass moving up from the equator collides with a cold air mass moving down from the pole. If the conditions are right, eddies are formed off these colliding masses and counterclockwise rotating circulation systems are produced. In the circulation system, air is coiled up through the cell and forced out the top. This counterclockwise rotating air mass is called a low pressure system, since all the air is being lifted up and out of the cell, producing lower pressure at the ground level. The air that is forced out settles in an adjacent area, forming or adding to a high pressure system. High pressure because it has more mass and weight. The air rising out of the low pressure system creates a void that is replaced by the air from the high pressure system, thus completing the cycle of air movement between the two systems. By placing a device that measures pressure in each system, we would of course record lower readings in the low pressure cell and higher readings in the high. If we connected lines to all those locations across the country with the same readings, a picture of the pressure systems can be produced. There is a constant movement of air between these highs and lows as they try to equal out their pressures. This movement of air is wind. The greater the difference in pressure between high and low, the stronger the wind. The difference is called gradient. Anytime you have hot and cold trying to occupy the same space, expect some unrest. When air masses of different temperatures and moisture content collide, the boundary between the two masses is called a front. A cold front is a cold air mass moving in to replace a warm air mass. A warm front is just the opposite, warm air moving in to replace cold. The first thing we need to look at with the passage of a front is how the winds behave. Generally, in the northern hemisphere, fronts move from the west or northwest to the east or southeast. Wind direction can change up to 180 degrees when a cold front moves through an area, 180 degrees being the opposite direction. To illustrate this, let's look at a fire that is burning under a warm air mass. The winds will generally be out of the southwest. When a cold front moves over this fire, the winds can be gusty and their direction can change abruptly and move from a south wind to a west wind or even as far as a north wind, which is the opposite direction as it was blowing before the front. In both warm and cold front passages, winds are usually strongest before and during the passage. The example I showed was a typical cold front, but fronts can move in from any direction. Typically, on the East Coast, it rains during most frontal passages, but there are times when a dry front moves through, which can cause some real fire behavior problems. Pay particular attention to the fire weather forecast when a front passage is predicted. Winds blow at all levels in the atmosphere. The winds at the higher levels are the ones that drive weather systems across the country. The jet stream, for example. The winds that are produced within a few thousand feet of the Earth's surface are very important. These winds, if they're undisturbed by the topography of the Earth, are called gradient or free air winds. If this gradient wind hits a mountain range that is perpendicular to its direction of flow, an oscillating wave pattern can develop on the lee side of the range. Called standing waves or mountain waves, These oscillating patterns can cause extreme fire behavior that can create control problems if they reach the ground. This lens-shaped cloud, called an alto-cumulus standing lenticular cloud, is an indicator that strong winds from a mountain wave are blowing above. If you see this cloud, plan a strategy in case the wind should move to the ground and over your fire. Let me illustrate another example of what these gradient winds can do. Let's say that this rock is a mountain range. When a strong high-pressure system builds, say on the east side of the mountains, and a low-pressure system is present over on this side of the mountains, the strong gradient or pressure differential between the two systems will cause the winds to blow over the mountains and down on this side. If these winds are warm and dry, they're called firn or gravity winds. As the winds rush down toward the low pressure area, they're compressed as they move down slope, causing a warming effect. Three things are at work here: strong gradient or pressure differences, gravity, and compression. By the time the winds get to the bottom of the mountain range, their temperature can be as much as 20 degrees warmer. They can be extremely dry and blowing as high as 30 to 50 miles per hour. Mix a fire with these winds and you have a major problem. In Southern California, these winds are the famous Santa Anas. Santa Anas are the most familiar, but this phenomenon occurs all over. In Central and Northern California, these winds are called mono or north winds. In the Pacific Northwest, they're called east winds. And on the east side of the Rockies, they're known as the Chinook winds. Gravity winds also form off the Appalachians. This infrared satellite shot shows the warmer, compressed gravity winds as a darker shade of gray. In the summer of 1990, the Dude Fire in the Tonto National Forest was hit by high winds from a thunderstorm that developed over the fire. This thunderstorm, along with some other factors, caused extreme fire behavior that overran a number of firefighters, 6 of whom lost their lives. Thunderstorms can cause extreme fire behavior. Whenever you see one in the vicinity of a fire, you need to take special notice and understand exactly what might happen and how it can affect you and your safety. Thunderstorms need 3 conditions in order to develop. First is unstable air. Second is moisture. And third is some triggering device to produce upward vertical movement of that air. This could be a frontal passage or by intense heating from below, such as the sun heating the ground on a hot summer's day, or by air being forced up the side of a mountain. A thunderstorm's life cycle has 3 stages. The first stage is when fluffy cumulus clouds start building vertically, caused by one of the triggering devices we mentioned. As water vapor changes into liquid, a tremendous amount of heat energy is released. In this stage of development, the upward motion in the cell is being fed by this energy. It is almost like a perpetual motion machine. Air from outside the cell itself is being pulled in primarily from the surface, creating updrafts. Eventually, the cell becomes taller than it is broad. This first stage is called the towering cumulus stage. On the ground, you might notice a slight surface wind shift toward the towering cumulus as the air is pulled up into the cell. In the second stage, called the mature stage, the fuzzy appearance of the upper part of the cloud, as well as its characteristic anvil-shaped top, make it unmistakable. At some point, the updrafts cannot support all the raindrops and ice particles, and they start to fall out. As they do, they drag air, which is the beginning of downdrafts. In part of the cell, the updrafts continue, and in another part, the downdrafts rush out. The appearance of virga is a visual indicator that the downdrafts have begun. Virga is precipitation that evaporates before reaching the ground. It should be noted that thunderstorm downdrafts can reach speeds of 50 to 70 miles per hour as they flow out of the bottom of the cell. The strongest gusts will be at the front edge of the storm. You can tell the front of the thunderstorm by the anvil-shaped top. It points in the direction the storm is heading. Lightning will be at its peak during this stage of the storm. As these updrafts end, we enter stage 3, the dissipating stage. With no more upward movement to feed the cell, the downdrafts quickly end, and the winds, temperature, and pressure all return to the condition they were in before the storm started. Thunderstorms can be deadly. Watch the developing storms, anticipate where the downdrafts will be coming from. Be ready to move to a safe position in relation to your fire. Of course, if life were easy, you'd only have to watch and be concerned with one thunderstorm at a time. Usually, however, there will be many cells in an area during any given period, all in different stages of development. So watch and plan as best you can. If you see this cloud formation in the early morning, it's a signal that moist, unstable conditions are present. This should alert you to possible thunderstorms in the afternoon. We call these clouds alto cumulus castellatus. Note the characteristic cloud formation in the form of turrets or battlements, like you might see on a castle. Local winds can develop off the ocean or large lakes. Because the sun's radiation is absorbed more deeply in water than on land, water tends to change temperature very slowly compared to land. When the sun comes up in the morning, the land heats faster than the water. This causes air to rise over the land, creating an area of low pressure. As it rises, it cools and falls back over the water, adding to a high-pressure system. Air from the high feeds the void left by the rising warm air, creating what by the ocean is called a sea breeze. At night, this process is reversed. Because the water temperature stays about the same, the land temperature falls below the temperature of the water, causing the air to rise over the warmer water and fall back over the cooler land. The land breeze that is formed as the air from the cool land rushes back to fill the void left by the rising air over the water is, of course, blowing in the opposite direction as the sea breeze during the day. Be aware of the effect these winds will have on your fire. Along the South Carolina coast, the sea breeze is well recognized. As the air flows inland from the ocean, a sea breeze front is created along with a very marked wind shift. Thunderstorms can develop with the passage of these fronts. Another example of a localized wind is one that is generated by the pressure differences caused by one slope of a mountain being warmer than another. Aspect is the direction a slope is facing. On this mountain range, as the sun comes up, the slope that the sun hits first is the east aspect. As the sun rises, these east aspects are warmed. As they are heated, both directly and indirectly by the sun, air will start to rise, causing upslope winds to develop. As the sun moves through the day, the south and west aspects also warm, causing updrafts to form on these slopes. Because the south and west aspects receive more of the sun's radiation, these slopes have the strongest upslope winds. As these upslope winds develop, where's the replacement air coming from? It's coming from lower down the valley. So we not only have upslope winds, we have up valley winds. As the sun moves off the different aspects and shading takes place, the winds will reverse and move downslope. Because the south and west aspects are the last to have direct solar radiation on them, they're the last to cool. This means downslope winds will start later on these slopes. On any aspect, the downslope wind is usually not as strong as the upslopes during the day. Downslope winds combine to form down valley winds at night. The key to local winds is to realize that they can develop in any geographical region. Anytime surfaces have a difference in temperature for whatever reason, winds will be produced. These winds will affect the direction and intensity of your fire. That is, assuming they're not overpowered by a stronger weather system moving through the area. Always check with a fire weather meteorologist on wind and weather patterns that are unique to the area of your fire. Moisture in the air or in the fine fuels has a pronounced effect on how actively your fire will burn. In our discussion of moisture, we'll look at relative humidity and how it relates to fuel moisture. A major point that you need to understand as we talk about moisture is that warm air can hold more water vapor than cold air. My breath is warmer than the air on the surface of this mirror. As I exhale, the warm air from my breath hits the colder surface of the mirror, and because this colder surface can't hold as much moisture as my warm breath, some of it condenses out. This sponge is saturated. It can't hold one more drop of water without a drop coming out. Air reaches saturation just like the sponge, and when it does, we get precipitation, fog, or dew. With a demonstration, we'll make a correlation between these sponges and the air in our atmosphere. This small sponge represents the amount of moisture air can hold at a fairly cold temperature, let's say 35 degrees. The large sponge is the amount of moisture this air can hold at a higher temperature, say 80 degrees. Remember, warm air can hold more moisture than cold air. So the small sponge can hold this amount of water at saturation, and the large sponge can hold, say, 5 times that amount at saturation. If we were to pour the amount of water that saturated the small sponge, the 35-degree air, into the large sponge, the 80-degree air, only 1/5 of the amount of moisture the large sponge could hold is occupied. So this 80-degree sponge is a lot drier than this 35-degree sponge with exactly the same amount of water vapor in each. From this demonstration, we can define relative humidity, or RH. Relative humidity is the amount of water vapor in the air divided by the amount of water vapor the air could hold saturated. That value is expressed in a percentage. Let's determine the RH during the hottest part of the afternoon. This represents the amount of moisture in the air over the amount of moisture the air could hold saturated. Remember, during the hottest part of the day, the air could hold a lot of moisture saturated. In this example, the air, when saturated, can hold 5 times the amount of vapor in the air. So we have 1/5 or 20% relative humidity. As the temperature drops off after the sun goes down, the moisture in the air stays the same, but the amount of moisture the air can hold saturated gets less. So we now have 50% RH. As the night moves to dawn, we reach the coldest nighttime temperature. Saturation at this temperature is again represented by the bottom sponge. As we showed earlier, the amount of water vapor in the air is more than the air can hold saturated. So we have 100% relative humidity with rain, fog, or dew. What you need to understand from all this is that at night and early morning, relative humidities are usually high. The air is wet, and as you might think, fires will have difficulty burning and could possibly go out in certain fine fuels. As the sun comes up, the temperature gets warmer and warmer. The amount of water the air can hold at saturation gets more and more. So we have RH that goes from 100% saturated air to 80% to 50% to, let's say, 20% relative humidity at the hottest part of the afternoon. As you can imagine, fires will be the most active during this hottest time of the day. Just remember, as temperatures go up, relative humidity goes down. The air gets drier and fires get more active. As the wetness or dryness of the air affects fire behavior, the wetness or dryness of the fuel the fire is burning in also affects a fire's activity. When the moisture content in a fuel is high, meaning the fuel is wet, fires are difficult to ignite and burn very poorly, if at all. With low moisture content in a fuel, dry fuels, fires start very easily, and with the addition of wind, can spread very rapidly. The daily change in relative humidity affects the fuel moisture in small diameter fuels or fine fuels like conifer needles or small twigs. This means that these small fuels can dry out during the course of the day as relative humidity goes down. By charting relative humidity and fine fuel moisture during the day, we'll see that fine fuels dry out as relative humidity decreases, only a little behind. What do you think the effect of daily relative humidity changes will have on larger fuels like this log? Well, probably not too much. What affects the fuel moisture in this log is how long moisture stays in contact with it. If the sky opens up and drops 1/4 of an inch of rain in 10 minutes, this fuel will probably absorb very little of the moisture and will probably dry out in a relatively short period of time. If that same 1/4 inch of rain falls over a period of, say, 10 hours, the log will absorb a lot more moisture and will take a lot longer to dry out to its previous moisture content. To sum up, low relative humidities and fuel moistures mean little moisture in the air and fuel. Fires can burn very aggressively and be difficult to control. If the RH and fuel moistures are high, fires can be expected to slow considerably and possibly even go out in fine fuels like grass. The stability or instability of the air around the fire can play a significant role in how that fire will behave. Atmospheric stability is defined as the resistance of air to vertical motions. High-pressure systems are like domes of stable air that are covered by a blanket. The sun heating the ground might start some air to rise, but unless the heating is fairly strong, the air won't break through that blanket. In the summer, large high-pressure systems form over the western half of the states and become stationary. These highs produce clear skies and warm, dry temperatures. Firefighters need to be aware of the fire behavior that can result from a phenomenon called subsidence. This high-pressure system is stationed over a western mountain range. Because of any one of a number of reasons, this air will start to settle or sink. As it does, it is compressed as it moves toward the ground. As it compresses, much like in the Santa Anas we talked about earlier, it warms. As we also know from earlier discussions, as the air warms, it gets drier. So we have this mass of warm air with low relative humidities moving down below the peak of this mountain. If your fire is burning above the level of the subsiding air, expect its behavior to be active. On the East Coast, subsidence air can develop in advance of a slow-moving or stationary tropical storm. This satellite image shows a band of warm, dry air on the outside of Hurricane Diana's rotation. Humidity in this area dropped below 25%, a significant departure from normal RH levels in this area, and, as you would think, greatly increases fire behavior activity. Another product of a stable atmosphere that we need to look at are night inversions. An inversion is a layer of cold air that is capped by a layer of warm air. At night, in a stable air mass, air that is cooled by contact with the earth will flow downslope and collect in valleys or basins with poor air drainage. If your fire is burning under the inversion layer, its activity will slow down considerably during the night because of cool temperatures and rising humidities. In the morning, the sun will warm this air, and as it reaches the temperature of the warmer air above, the inversion will break. This causes the warmer and drier air on top to mix very rapidly into the air below. Watch your fire as this inversion breaks. Activity can accelerate extremely fast as this mixing takes place. Let's talk for just a minute about this warm layer that is the cause of the night inversion. Remember, downslope winds are settling cool air into the valley floors. By measuring the temperature at different spots on the way up the slope, we find that the temperature increases to a point and then decreases again as we keep moving up. This warm area we found in the middle of the slope is called the thermal belt, and it contains the warmest and driest air on the nighttime slope. A fire that is burning in the thermal belt can burn with intensity and not slow down as much as a fire normally would at night. Fire activity could remain high. We've learned that cool air is dense and flows downslope like water. It pools in pockets and valleys. If your fire is burning in this cool layer, think about what's happening to its smoke. We've talked a lot about how warm air rises, but what happens when that warm air reaches a level where the temperature is the same? Well, it's not going to rise anymore. It'll level out at that height and spread horizontally. So, the smoke will be trapped under this warm inversion layer. Visibility, the health of the public, and yourself may be adversely affected by the smoke and other pollutants in this trapped air. In finishing off my discussion of atmospheric stability, I'll show you some indicators that can clue you into, first, a stable atmosphere, and then an unstable atmosphere. If the surface winds are light, or if you notice haze or smoke hanging near the ground, you're probably looking at stable conditions. If you see clouds like these, stratus clouds, this is another indication of a stable atmosphere. Note there is no evidence of vertical building. In an unstable atmosphere, any upward movement of air is enhanced. A stable layer near the surface can become unstable if heating from either the sun or a wildfire is strong enough. When the air is heated to a high enough temperature, it can break through the stable layer, or the inversion, and a free-moving vertical column can develop. A dust devil or a whirlwind is one of the best indicators of an unstable atmosphere. Fires can generate their own whirlwinds because of the accelerated vertical movement of air. We call whirlwinds and fires fire whirls. As fire whirls develop, they pick up loose burning material. The strong updrafts carry that material up and out in front and to the sides of the fire and drop it. The material can start new fires away from the main body of the fire. These fires are called spot fires. Unstable conditions are characterized by gusty winds, dust devils, hot days, and cumulus-type clouds. Weather plays a very significant role in the behavior of a wildfire. In order for a firefighter to do the job safely, he or she must always be aware of the weather and understand how changes in the weather can affect the fire. We've briefly touched on the topics of wind, moisture, and atmospheric stability. All of these factors are important and often act together. It is impossible to isolate individual weather elements, but if you learn to tune in to the fire weather forecast, it normally addresses wind, moisture, and atmospheric stability, and gives a clue as to how they'll react on any given day. To ensure your safety and the safety of those around you, hone your senses to the weather. Be sure you know how the fire will react when the wind increases or changes direction, the humidity changes, or an inversion suddenly lifts. Unexpected or unforecasted weather changes do occur, and if a fire weather change causes an increase in fire activity, be prepared to take action to provide for your safety as well as the safety of others around you.